Welcome to the reliability and availability of centrifugal pumps, how to extend pump uptime. This is the latest in the series of webinars by Trillium Flow Technologies. With that, let's move on to the next slide, please. So just before I introduce the speakers, just to remind you that the chat is open for questions and answers. I see we've already got one. And, you know, as we go through the webinar, if you have a question, please put it in the chat. We have time at the end where we will try to address any questions that are posed by the audience as best we can. So with that, let's introduce the speakers. So first off, myself, I'm Simon Bradshaw. I'll be introducing the webinar and giving you a brief introduction to Trillium Flow Technologies. I'm the Director of Engineering and Technology for Trillium. I look after essentially all of the sustaining engineering as well as the new product development across the whole of Trillium, and all the attendant procedures and requirements that go along with that. I've been in the pump and valve industry my entire career. I have the world's most boring resume or CV as a result of that. And I've worked, as you can see there, with a whole host of companies in this space. And now, finally, of course, with Trillium. I hold a degree in mechanical engineering, and I'm a chartered engineer in the United Kingdom. So next, I'll introduce Ralph Cohen, who will be doing all the heavy lifting and technical detail of this presentation. Ralph has 17 years of experience, and he currently serves as a rotating equipment engineer with Trillium. His work currently, focuses on centrifugal pumps, the systems that they're in, and essentially troubleshooting RCAs, fixing customers' problems is in short. He also holds a Bachelor of Engineering in Mechanical Engineering and is also a chartered engineer. So with that, let's go to the next slide. So this is a little bit about Trillium Flow Technologies. What we typically hear is people haven't heard of Trillium, but they may have heard of one or more of the brands that we have. So this is just, again, to kind of link the two. So on the pump, we have pump brands and we have valve brands. On the pump side, I'm sure a number of you will have heard of Begeman, Flowway, Gabionetta, or our most recent addition to the family, which is Termomeccanica Pompe in Italy. So those are all, I think, pretty well-known brands within the industry. On the valve and actuator side, we have Atwood and Morrell, based out of the USA. We have Batley, Blakeborough, and Hopkinson's, which are based out of the UK. Sebeam and Saracen, which are essentially safety valves based out of France. And our most recent addition to the family is Redpoint Valves, which is based in the Netherlands, making custom valves for difficult applications. What you can see on the right-hand side is our geographical makeup. We have around 21 facilities around the world, in all parts of the world, as you can see there, plus a global network of third-party sales and authorized service centers. This enables us essentially to be wherever you, the customer, are, and to provide the necessary support and, whether it's technical or spares or commercial, for our products and to suit your project needs. If you want to go to the next slide, please. So like a lot of companies in this space, although the Trillium name is relatively new, we've been around for a long time. As you can see there, around 190 years, if you follow the very extended timeline. That said, we're continuing to add new products and services, which are essentially focused on making you, our customers' processes more efficient and productive. And I'd like to highlight on that timeline in 2020, that's when we added Redpoint Valves in the Netherlands. And then a year later in 2021, we added Termomeccanica Pompe to the family. So with that, let's go, that brief introduction about Trillium, let's go on to the next slide. On the pump side, which is what we're kind of focusing on today, this is just to point out that we pretty much make almost every type of pump that API 610 or HI has a definition for, and a few that they don't, such as the Rotajet, the pitot tube pump. So you can see the designations there. I'm sure they're familiar to many people in the industry in terms of overhung between bearings or vertical. On the right-hand side, it's just to emphasize that these are the main segments that we participate in: oil and gas, water and wastewater, power, and general industry. So with that, let's move to the next slide. So the agenda for our webinar today, and this is where Ralph takes over. First of all, we're going to define reliability and uptime. Then we're going to talk about why they matter, ways to improve reliability and uptime. Then Ralph will present a couple of case studies for which are good to kind of ground the whole exercise. There'll be a recap, and then there will be time for any questions and answers at the end. So with that, I'll hand it over to Ralph.
So, hello, good morning, good afternoon, good evening, depending where you're sat in the world. And as Simon said, thank you for the introduction. We're talking about reliability and uptime of centrifugal pumps. Okay, so what is reliability? It's essentially the ability of a system or your equipment to function without failing. Obviously, you don't want to be nursing your kit through to the end of the day, the week, the month, or perhaps thought even the year. So obviously reliable equipment will run continuously and happily. So what is uptime? It's essentially a measure of that reliability. The longer the uptime, the more reliable the kit. The two, you could argue the two definitions are almost interchangeable, but the bottom line is the longer your kit runs without failure or needing to maintain it, the better. Okay. Obviously, reliability and uptime matter. If your pump isn't running, you don't have a process. If you don't have a process, you're not making product. If you're not making product, your company's losing money, okay? So what, generally speaking, will stop a pump or your process? There's two main things. The main one is obviously planned maintenance, where you shut the process down in a controlled manner. You do planned servicing, you have the spare parts to hand, you've ordered in the bits. You shut down for a day, a week, however long it takes, and you generally will go through and service everything in that shutdown process, while obviously you don't have the hazards of maybe heat or pressure in the way. The other one, of course, is the dreaded unscheduled stoppage, or as we maybe commonly call it, a breakdown. Okay, obviously these are unexpected. They can cause problems. They can cost a vast amount of money. If a process has to shut down quickly, there could be waste products. We could be, if you're a power station, maybe lost generation. Either way, you're looking at potentially big losses. Okay. Bottom line is no pump, no process. Okay. So through the first few, or the first half or so of the PowerPoint, I'm just going to sort of compare this to a car. We're all, I'm sure most of us will have a car or a vehicle of some description, whether it's a bike or a whatever, or a van, maybe a works van. And you'll know that there will come a point where you have to put that vehicle in for a service. You can plan for it. You can hire another one to get you the day. You could maybe take the bus to work. You can plan for not having the vehicle. The problem, of course, lands where the vehicle leaves you at the side of the road. You're going to miss your plane. You're going to miss your meeting. You're going to miss your holiday, whatever. Obviously, a breakdown, an unplanned stoppage, obviously is a lot more inconvenient, and obviously, in the case of a pump, expensive. Now, there's quite often I hear on my tours around various customers that they just don't build them like they used to. They're not as reliable as they were. And there is a bit of science behind that, in that our forefathers obviously didn't have the CFD and all the computing power and calculations and modern material production methods that we have now. And so things tended to be over-engineered. I use here as a wee example, nothing to do with pumps, the Forth Railway Bridge. not too far down the road from where I'm sat here in Alloa. And in 1883, it was designed to take trains of roughly 800 tons. Today, bridge is still standing, and they're running trains of nearly 1,500 tons over it. And why is that? It's because they've gone through with modern techniques, obviously checked the metalwork out, made sure that there are no cracks, etc. And they've now calculated that, yes, it is capable of handling nearly double the load it was designed to take and still do it safely. Having said that, of course, it still needs maintained. Now, I'm sure a lot of you will be aware that a centrifugal pump and the system that it works in are inextricably linked, okay? You cannot separate one from the other. The fluid going through the pump goes through the pipes, the filters, and everything else. And so the two, or the whole system has to be looked at as a whole, okay? Very often, the pump will be the point of failure, but also very often, the reason the pump has failed is actually to do with something else in the system. And again, we'll have a look at that in a bit, in a few slides' time as well, okay? As a colleague of mine who's now retired used to say, the pump is generally always guilty until proven innocent. So what can cause the system to change and to start the pump reducing its life expectancy? Generally speaking, it may not be operating optimally. If it's not running at its design duty point, then obviously it's going to be using more energy, it's going to be running less efficiently, and of course that less efficient operation will then mean more vibration, more heat, and generally speaking will reduce the life of the components in the pump. Taken to extremes, obviously wear and cavitation can cut in. This is an impeller we took out of a pump that had obviously not been running at its duty point, and you can see the damage caused to the vanes there by not running at that optimal level. We have a chart here. Some of you may have seen it on one of Simon's little posts on LinkedIn. The life cycle costs of a pump. What we have here is a chart which is an approximation. Obviously there's many pumps out there. Everyone will have its own hard data, but very roughly, this chart shows the costs of running a pump for the first 10 years of its existence. And you can see the top from say 12 o'clock round to 2, you've got the initial purchase of the pump. Going round, we have the installation costs. Obviously they tend to be fixed. But when we start to come round to say from about sort of 4 o'clock onwards, we then get into the area of the costs which can and are affected by maintenance. We obviously have the maintenance itself shown in grey there. That's your downtime. That's when the pump isn't running. Maintenance itself can be upwards of 20% of the cost of the pump, whether that's the cost of the components or the team who are disassembling it, reassembling it, etc. The biggest chunk of the cost, however, is, of course, your energy to run the pump. That's the big dark blue from roughly sort of 8 o'clock back round to 12. So you can see that there's a sizable chunk of your costs are all down to how efficiently and how well that pump runs, okay? So how do we improve this reliability and the uptime, how long the pump is running for? Obviously, maintenance is your main thing. So of course, back to the car, older cars, you had the little light that came on and told your engine was knackered. Usually by that point it was too late. Of course, I'm sure most of us will have had an old car at some point, whether it was our first car or whatever. And of course, you'll have the lights coming on, the oil, the temperature, etc. Usually by the time that's happened, you need to turn off and phone for a tow truck. Of course, pumps also traditionally have been instrumented up. Again, generally vibration and temperature are the two that usually were alarmed and would trip the machine. Also, some processes also use monitoring of the head and the flow. If either of these are off where they should be, again, they could be used to fire alarms. And of course, traditionally, because again, computing has evolved remarkably over the last 15, 20 years, where maybe something was built, maybe a power station in the 1960s, you might get some warning lights on the control panel. We can, of course, now have advanced warning. And again, we'll look at that later. Okay, so we need to keep the pump running efficiently. And of course, the thing you do with air is scheduled maintenance, okay? Traditionally, this was performed on a time basis. You see the graphic there, time to service it. And your pump manual would give you X thousand hours or X hundred hours between service, depending on the duty of the machine. But is this time interval appropriate? For example, if you're servicing your pump every, say, 1,000 hours, and you take it apart, you've bought a nice new mechanical seal, you change it out, you take the old seal back to the office and you look at it and you think, there's nothing wrong with this, it's got another at least 1,000 hours on it. You could be replacing components unnecessarily. Obviously, there's a cost, okay? Other thing, of course, we have to worry about these days, our environment. If you're replacing components unnecessarily, you're also scrapping them potentially unnecessarily. And that generates waste, which again costs money to dispose of. And of course, there is the big cost, of course, is employing the team to take the pump apart and put it back together again. Potentially even shutting your process down for 2-3 days, a week, however long, for no reason, okay? So again, your scheduled intervals may not necessarily be appropriate for the way your pump is running, okay? Because let's face it, if you can service the machine every other outage rather than every outage, there's a cost save. Excuse me. Okay, so I guess as we're all engineers, we're probably all familiar with the bathtub curve, which indicates failure rate over time. Now, the bathtub is, as we know, made up of three essentials, or three sections. The one that we have next to no control over is, of course, random failures. Obviously, by doing root cause analysis, you can find the results of these failures and hopefully prevent them happening again. Towards the left-hand end is where, again, I'll go back to the car. You buy an old car, you expect to have to replace more components than you would if you bought a car with a very low mileage or kilometre count. Okay, longer it's been running, the more wear-out failures you'll get. Parts wear, they need to be replaced. Tyres are an obvious example in a car. You also have early failures, and these are failures which are due to the machine maybe not having been assembled quite correctly, or various other factors, which again, we could probably spend another webinar discussing. However, of course, the other problem with scheduled maintenance, if you're repairing the pump, you're instantly, as soon as you bring the machine back online, you're in that potential for an early failure. Seal may not have been fitted correctly. Obviously, you would go through your quality processes to make sure it is. However, things happen. Yeah, we're all engineers. We've all experienced things like that. And so again, if you can avoid disrupting the machine when you don't need to, again, there's another potential downtime that you've removed from the system. And I've just realized I've talked through the slide here without actually putting any words up. Okay, so I was talking about the random failures in the middle there. And very often, as I say, because the pump and the system are inextricably linked with each other, very often we have found, as Trillium, if we've gone to assist a customer with a repeated failure, that the failure of the pump, as I say, is more the symptom rather than the cause, okay? But, excuse me, and this is why, again, it's always well worth whatever failure you have, go back and do a good analysis of why it's failed. Again, it would stop you, having the same problem soon. Now, I was talking about data. You know, we monitor generally vibration, temperature. There's usually a pressure gauge, even if someone's walking around with a notepad once a week. We can take data on how that pump is performing. And by extrapolating and using that data based on historical evidence, we can then interpolate an advanced warn of servicing. Now, I guess some of you will have a more modern vehicle. You may have messages like this where it's warning you that you need to change the oil rather than just the oil light coming on and saying, get me to the garage quick. Yeah, obviously back to the cars. But again, we can use this interpolation of the data on our pumps as well. We can monitor the pump in real time, and by taking note of how worn parts have been when they've come out, we can potentially give advanced warning of maintenance requirements. You might notice a temperature going up before something fails. You can then use that as an alarm that the bearing, the seal, whatever might be on its way out. And likewise, as we discussed earlier, it may be you're servicing a pump too often. You can use your data if you're servicing parts that are perfectly good for more use. You can then optimize your scheduled maintenance actions. So we also have the other issue, of course, pumps potentially breaking down repeatedly before their next service. And why does this happen? Again, as I said, the pump and the system, I keep repeating this, but it's a fact of life. The two cannot be looked at individually, okay? So maybe if you've got an older pump, an older system, there's plenty of kit out there. Oil and gas refineries, for example, built in the 1950s, still running, still with the original pumps as supplied back in 1950. Power stations, obviously a lot of the coal-fired ones, certainly across Europe, are being replaced, but nuclear, for example, they run for 30, 40 years in some cases. You could have older kit, which may not be running the way it was originally designed. Now, that could be because process requirements have changed. Maybe in a production process, you want to sell more, or very often in the case of oil and gas, if a well starts to deplete, the oil coming out the well changes viscosity, changes density, which affects the operation of the pump. And very often there's just less of it. And again, the pump isn't running at the place it was designed or the point it was designed. Likewise, new pumps can also suffer from not matching their system. Very often system designers will make the pump just a little bit bigger for a bit of contingency. Now, of course, that's all well and good in theory, but of course, we'll see in the next slide or two that operating a pump not at its design duty point can, in some cases, have some very drastic effects on its life expectancy. I'm talking about system changes here. Again, there's the ones you would expect. Things like blocked filters, failing coolers, your fluid's warming up, it's maybe changing density, viscosity because it's warming up. And just good old corroded pipework. What started out as an 8-inch pipe might now be a 6-inch pipe if it's badly corroded. And obviously, the smaller your pipes get, the more corrosion will affect the flow through them. Okay, so how do these system changes affect your mean time between failures? Okay, well, bottom line is, as I said already, if the pump's running less efficiently, your wear rates are, of course, going to increase. So this graphic shows us where the energy going into a typical centrifugal pump, how it's dispersed within the pump. We're all engineers. We all know that there is no such thing as a 100% efficient machine, and pumps, like all other machines, fall into that category. So number one on the graph here, the big purple blob, you can see is the pump's output. So that's the energy that's going into either moving or pressurizing the fluid, depending what the pump is designed to do. You might not be surprised to see that it peaks at the 100% capacity. And I've just realized I forgot to explain the axes here. So the horizontal axis, as we're looking at it, as it says, capacity of the best efficiency point. Best efficiency point is also commonly known as the duty point or the nameplate duty point. It's generally the head and flow of the pump that you'll see tapped or teeped or etched into the nameplate. That is the point that the pump was designed to run at. Up the side, we have a percentage of the power that is being supplied to the pump through the coupling. Now, you'll notice that it bottoms out at 60% of the power, and that's because the lines, the yellow, green, red, and purple joints basically will head down towards the zero line, and it just would fill the slide. So, back to where the power is going. The big purple blob, number one, that's your power, obviously at 100% efficiency at the point it was designed. Fairly intuitive. You're going to get as much of the power going to the fluid as you'll get. So let's now look at the red and the green stripes above that. These are the hydraulic losses through the machine. So these are kind of almost like pipe friction losses through the passageways of the impellers, the diffusers, the casing, etc. Okay, so as you can see, as you go higher than your design flow, obviously just like standard pipe friction, you get more loss through there, through this effect, and you can see those lines broadening out. Likewise, if we go the other way, it's like reducing the flow through a pipe, and you can see they fall off remarkably quickly. And as they're falling off, there is, however, one big energy loss, which is usually the one that will kill a bigger, higher power machine, higher power pump. And that's number 4. That's recirculation. Now, what recirculation is when you maybe haven't closed, or you've purposefully closed the discharge valve. Obviously, your centrifugal impeller is trying to throw the fluid clear, and it's got nowhere to go. But it's got energy, it's got movement, it has to go somewhere. So it basically does a U-turn and comes back down the inside of the impeller. And as a result, a lot of fluid ends up going round in circles inside the impeller passageways. Now, of course, this is inefficient. We're putting energy into this fluid. And as we all know, one of the main things that waste energy turns into is heat. Very quickly, you can boil the contents of the pump. And again, potentially for another course, the wear rings of the pump act, generally speaking, as small journal bearings. And of course, if you've just boiled the contents of the pump, then those journal bearings cease to operate as small journal bearings, shaft starts to flex, and very quickly you'll get a pickup and a seizure. Big high power pumps, boiler feed pumps, maybe water injection pumps in oil applications, oil and gas applications, where you're talking lots and lots of megawatts to power the machine. Obviously, this can happen in a matter of seconds, yeah? And this is why many pumps have leak-off systems to ensure there is always flow through the pump. Again, that's probably another subject for another discussion or another webinar. The other losses that we see across the top of the graph, generally speaking, stay constant. Number 5 is kind of related to the recirc flow. That's really just the fluid returning back through the wear rings, which is obviously a gap that needs to be there. The light blue across the top is your mechanical, and you can see that only tends to get bigger when we're way off design, and that's usually down to the thrust bearing having to do more work. So hopefully we can see how not running the pump at its best point will generate a lot of losses and heat. Okay, so plant changes. We've talked about that, whether it be, as I say, corroding pipe work or whatever. But what we have here, just as an example of almost literally the wrong pump as a result of a plant change, was a coal-fired power station not too far from one of our service centres back in the day. I believe it's now a grassy field for emissions reasons. but it was originally designed in the early 1960s, and it was designed as a base load station. In other words, they turned the boilers on and ran them for 9-10 months at a time without turning them off, 24/7, 7 days a week. In the year round about the early noughties, obviously emissions were becoming a big thing around Europe, and so a lot of the coal-fired stations were being replaced by wind farms and other more environmentally friendly power. Net result, of course, was that the coal stations were sort of backed off to being what we call dual shifting, or basically being turned on at breakfast time for all the kettles and toasters and things that get turned on at breakfast time, and then being turned on again at the end of the day when everyone's got their ovens, their cookers switched on, cooking their evening meals. So what was happening was the pumps were being switched off and on maybe 4 times a day rather than once or twice a year. And of course, what happened there as a result of that, the feed pump reliability fell drastically. We were at one point seeing a feed pump through our service centre once a month. And why was this happening? As I say, change of operational needs, traditionally 9 months or so between turning off and on, but then being turned off 2 or 3 times a day. Okay, so why was this happening? The original pumps were designed with a balance device that we call a balance disc. We diagram here shows that impellers obviously have a low pressure and a high pressure side. And as a result, when you put 4, 3, 4, I'll get 3 in the diagram here, all in line, you end up with a net force trying to pull the rotating element of the pump towards the suction. Okay. We balance this hydraulically by putting a disc, obviously this is sealed in a casing, etc., and by making the gap between the dark blue sleeve bush and the disc very small, you can generate very, very low leakage through that balance device. And the device works basically on the pressure force area equations. So by sizing the disc and knowing the pressure generated at the discharge of the pump, and likewise we connect the right-hand side in this diagram round to the suction, we know the pressures, we know the areas, and we can therefore generate a force to counteract the impellers. We can balance that very, very, very well, and so you don't need a big thrust bearing. Now, of course, the problem with centrifugal pumps is that, as I'm sure most of you know, variable speed drives, if you want to reduce the output, slow it down. Of course, if you're turning the pump off and on, you can imagine a big boiler feed pump driven by a steam turbine does take a couple of minutes to wind up to full speed. And during those 2 minutes, the pump is not running at its optimal hydraulic balance. Now, that was fine if it was only doing it maybe once every 9-10 months, but start doing that twice a day, and very quickly your thrust bearing wears out. The punchline for this story is that there was another power station which had very similar pumps, same manufacturer, same number of impellers, roughly the same head and flow, but the difference was the other station was designed as a top-up station, so it was designed for dual shifting. And you can see the diagram we've got here on the left, the balance disc. That little tiny axial clearance obviously keeps you nice low flow. Diagram on the right is what we call a balance drum. Now, a balance drum uses a very different method to hydraulically balance or axially balance the shafts. It works by allowing water or the fluid to flow through the gap between the drum and its bush. And essentially the theory here is if you get the surface roughness correct, you're effectively doing the reverse of pipe friction losses. So you're forcing the fluid through the gap, high pressure on the back of the impeller there, low pressure obviously connected round to the suction. And so by forcing the fluid through the gap there due to the pressure difference, that fluid will try to drag the drum towards the discharge end of the pump as it's flowing through. Now, of course, standard fluid through small gap theory, If your pump is running at, say, half power, half speed, the pressure at that discharge will be less. Net result, there's less flow across the balance drum, and so the balance drum arrangement follows that pump performance a lot more closely than the balance disc, which does rely on absolute pressures. So by changing and basically taking the balance arrangement from the scrap power, or the closing power station, and replacing it, we got the life of these pumps back up to years on end between services. Okay. Now, again, this is obviously a very drastic example, you know, massive philosophy change in the operation of the power station, but also a big change to the pump. Obviously, smaller changes can and do help in the longevity. Okay, analysis of the data. This one again is to try and hopefully illustrate the point I was making earlier about the system being inextricably linked to the pumps, and the pumps generally being the point of the system that will fail first. What we had here was and again, another power station. They're big and high power. They tend to show these things a lot more easily than smaller machines. But basically, the pump started vibrating, and the station was very, very, very close to basically shutting the boilers down and pulling the pump cartridge out to find out why it was vibrating. So they called us in to investigate the pump. And so, of course, as always, we asked for the plots data, you know, temperature, vibrations, all that good stuff around the pump. But we also asked for any system data for anything round about it, valves, flows, temperatures, you name it. As you can imagine, we got a bucket load of data. And I should add, this graph is much reduced in the number of channels we were looking at. However, we narrowed it down to these, and you can see the brown trace there has a big old spike. So we thought, well, there's something been happening here. Let's have a look. So we asked for a zoomed in copy, and this is what we got. I shan't bore you with the analysis, but the long and the short of it was we realized that the boiler, that the feed pump speed was hunting, i.e. it was going up and down and up and down. And following a bit of investigation, we also realized that the steam control valve to the steam turbine driving the pump, you all still following, was basically what appeared to be what was leading each of these vibration peaks. So they went off, investigated the valve, which was a good 100 meters or yards away from the pump and the turbine, and lo and behold, they discovered that the linkage between the actuator and the valve had shaken loose. Okay, here's the thing. Hang on, why is it not fading? Oh, there we go. So bottom line was that they had checked that valve 3 weeks before the vibrations started. Nobody thought it was the valve, and they nearly shut down a boiler and pulled a pump cartridge. Anyone who's involved in power will know that that was not going to be a cheap decision. Okay, and this was a one-off case. It was a loose valve linkage. That the station did start doing other checks on their valve linkages as a result, and obviously this issue didn't happen again. But if you take nothing else from this little story, what we can see is it was a valve that was causing the issue, okay? But the symptom was the pump, okay? Again, as we say, system changes, the pump may be underperforming down to some other system issue. So don't ever, just pull your pump randomly. Okay, so where we're going with this is we're looking at data. We're using data to, excuse me, I'll start that sentence again. We're using data to look at our service intervals and how effective those are, okay? We can use data to predict a failure point and use that historical data to potentially change your maintenance schedules, again, for more efficient operation of your plant. Again, this is a subject all in itself, but just briefly here, we have a representative plot. You can see the alarm and the trip settings. These are concepts that have been around for decades. Very often would have just been a thermal switch or something to trigger an alarm. But if we trend the data for the pump over time, we can see section A on the left here. Now, again, should explain the axes. X-axis along the bottom is time. We could be looking at days, weeks, months, years, depending on how reliable your machine is. And the Y-axis, the vertical axis, could be vibration, temperature, or anything else that you're monitoring. Typically vibration and temperature. So section A, pump's just been repaired. It's running fine. Nothing's worn. It's running nice and steadily. And then obviously through time, things do start to wear, and you'll see your temperatures, vibrations maybe increasing slowly. Traditionally, before we had all these high quality monitors and high bandwidth recording and everything, section C is where traditionally you might notice it starting to make a bit more noise or get a bit warm or whatever. But this is where, again, you can then interpolate, use your interpolations to start booking your spare parts for the service. And obviously, section D is where you very rapidly would go into failure mode. Obviously, days of yore, you get the alarm. Hopefully, you'll never get to section D if you're using interpolated data. Okay, so as I say, I've just a slide to say what I've just said here. By using your historical data and analyzing it and trending it, you can set up some real-time, advanced, warning, oil change required type maintenance. And likewise, you can use it to alter your scheduled maintenance intervals to a more appropriate time for your plant. Okay. So, as I say, main savings here are process downtime and better use of your equipment, personnel, maintenance teams, etc. Okay. Again, by using the data, you can also look at root causes. It may not be the pump that needs repaired. However, it may also be that your pump is now not running where it used to and where it was designed to. Hence, potentially come talk to us. You can have a look on our website. I believe our re-rate webinar is up there for perusal if you missed that last month. But as I say, pump and the system do need to be talking to each other. So, summary, what I just said really. Reliability is crucial to keeping your processes running, keeping you in profit. Your pumps do have to be matched to your system, and they do have to be well maintained and operated correctly. Okay. So I think now probably is a good time to head to the questions.
Yeah, thanks, Ralph. So we do have some questions. If it's okay, I was going to take the first one. If you want to think about answering the second one on minimum flow bypass. So there's a question on what is your recommendation for starting up a centrifugal pump to minimize dry running and to avoid cavitation? What I'm going to do is actually the same questioner asked or had another question, so I'm going to combine the two just for the purposes of time here, where the questioner also asked, he's saying Norman Lieberman, which is a refinery troubleshooting engineer, coined the term starting NPSH, which is defined as the amount of energy needed to accelerate the mass of fluid in the suction line when the pump is initially started or off. Are you familiar with this term? So they're kind of interlinked, and the answer is yes. I actually wrote an article about this, which I'll post a link to in the chat in just a second. And essentially, this is a miss by Hydraulic Institute in their NPSH margin standard. They do not. They consider cavitation and NPSH as being a steady state thing, and in fact they are not. And there was a specific instance that I write about on a hydrocarbon project with a very light hydrocarbon where The pumps, there was a very long line leading to the pumps, suction line, several hundred feet, or I think around 100 meters or so. And the pumps were started as a direct online start. And what happened was the pumps would go into full pressure breakdown because the energy required to accelerate the fluid resulted in there being essentially no NPSH margin anymore. So the short answer is yes, absolutely, you need to consider it. HI I've talked to them, they say they will look at it for the new edition of the NPSH standard. I have yet to see exactly how they're going to deal with it, but it absolutely is something that needs to be considered. So back to the question of recommendations for starting up a centrifugal pump to minimize dry running and avoid cavitation. That's a pretty big question. I mean, it really depends a lot on your setup. If you have small pumps that are handling, something, say like ambient temperature water, you probably don't, and it's a short run, you probably don't care. You could start them up with almost no precautions whatsoever. As Ralph had pointed out, when you have big pumps handling hot fluids or where the energy is substantial, then you've got to consider your startup sequence so that you don't get into a situation either where the startup energy to accelerate the fluid initially results in total breakdown, or that you're potentially running the pump too long at or near shut valve where the pump will overheat. And Ralph's diagram from earlier, I think, calls that out pretty well. So yeah, there's not one size fits all, unfortunately, and you very much need to work with the pump vendor to. What I would suggest that you do is that you have an active discussion about, here's the protocol that we're planning to use to start the pump up. What do you think? And generally, the tier one vendors are going to give you an answer. They're at least going to look at the proposals, and if you give them details of your system, they're at least going to be able to give you some advice on things to watch out for and what might be critical for that particular service. So with that, I'll stop and I'll let Ralph, if you want to take the question, which is how should you set up the minimum flow bypass line when starting up a centrifugal pump? Do you want to take that one?
Yeah. Okay, yeah. And now, again, this is one going back to what Simon just said. If you've got a critical flow or a minimum flow bypass line, then that will, I would hope, would have been suitably sized by the pump's vendor in the first place. Obviously, the pump designer will know what the minimum flow through that machine needs to be, and would obviously set that up to suit the pump. Now, whether you want to change that or something is another discussion. But very often these bypass lines are maybe more in there as a safety margin, because if you think about it, while the pump is starting up, everything's cold, it's not running it until it gets up to speed, full head, etc., etc. And again, this is where you then obviously would need to get into your control system. At what point do you open the discharge valve? What other system effects? Obviously every system is different. So yeah, setting it up, definitely talk to your pump vendor, because obviously they know the machine, they know how far off that optimum operating point that you can go before disaster strikes.
Yeah,
answer the question.
I would just note there's a good paper in the Turbo Machinery and Pump Symposium proceedings on how quickly the temperature can rise even in a small pump if you operate it at shut valve. It's from quite a few years ago now, but it's one of the co-authors was a guy called Jerry Quill. You can look him up. I'll put a link to the proceedings if I can get there in time. But yeah, it's pretty scary even for pumps that are 50 kilowatts, also how quickly you can actually heat them up. Hence the need for the bypass line.
Indeed.
So,
sorry.
yeah, go ahead. Sorry, go ahead, Ralph.
I was going to say the flip side of that coin is that there are other pumps which will run forever and a day against a closed valve.
Yeah.
So each machine needs to be looked at. There is no broad sweeping cover-all statement. As I say, centrifugal pumps, they are unique to themselves and the system they're in.
Yeah, talk to your pump vendor. They should be able to tell you what will work in a particular instance. Okay, the next question is, when the OEM recommends certain hours to replace certain parts, what is the normal OEM safety factor in their given numbers? For example, a seal change every 20,000 hours. If I would extend this due to production constraints, it's good to know if you consider a certain range. I'll weigh in a little bit, and then maybe Ralph can as well. So the challenge here is oftentimes we don't get good data on what are the actual run times that are being attained for critical parts like seals and bearings, for example. So the way most OEMs will do it is they need to follow a standard like API 610, which says you're aiming for at least 3 years of continuous running. And they will design those parts so that they can attain that. The vast majority of pumps will attain that. Let's say less than 1% are going to require maintenance before that time occurs. Now what safety factor is in there? That's a bit difficult to say because it very much depends on the process conditions that they're exposed to. And though, again, just unfortunately, we're like a broken record here. Me and Ralph always say it depends. So the safety factor, unfortunately, depends. But generally, you could run them past that, particularly if you have, let's say, optimum conditions. Keep in mind, most of these are designed to operate off BEP. So the closer you can get to BEP, you can absolutely probably extend your run times by a factor of 2 or even 3 potentially if you operate very close to BEP. Sorry, Ralph, do you have any comment on that?
You've pretty much said what I was going to say. So yeah, I mean, there's not much else I can add to what you've just said. So
all right, let's see. So what do we got next?
I think the next one may have been a misunderstanding. I didn't say that you don't have to do scheduled maintenance. All I was saying was that as we've just to come off the back of what Simon's just been saying, if your pump has been running at its best efficiency point, there is a reasonable chance that most of the recommended changes may not necessarily be required. Now, yeah, warranty, yeah, do what it says in the book, because if it fails, you're hit. Yeah.
Yeah, I mean, it's just
for the avoidance of doubt, I didn't actually say you don't have to do the scheduled maintenance, but certainly if your pump's under warranty, do what it says in the book. I would recommend that for any machine, even the washing machine in your kitchen.
I mean, it's as Ralph says. I mean, we're on the hook for warranty as the OEM. Given that we don't have, the pump is a slave to the system, as Ralph had outlined earlier, we don't have control over where somebody is going to operate this. So we set a fallback of a minimum maintenance schedule. Now, if you analyze the data, as Ralph also talked about, you can certainly go beyond those scheduled times, but you need the data to back it up, as he outlined. You can't just do this blind and hope that it's going to work out for you. All right, let's see. Next question. For non-automated condition monitoring of temperature, vibration, and other pump performance parameters, what frequency do you recommend for these manual checks? Oh, that's an interesting one. You want to take that one, Ralph? You want to go first?
Again, a lot of it will depend on your system, your you know, how many spare people you've got to go around and write down what's on the gauges, and you know, again, this is another one of these kind of case by case ones. Obviously, the more the better. The more data you've got, the better analysis you can do on it. You know. Even just to compare it to, say, an automated system, for example, say you were monitoring taking a snapshot every hour, your pump could be going through 36 vibration cycles, and you'll miss them all because it just might be on a low vibration as that data point is captured. So obviously, if you up the sample rate of an automated system, you're more likely to catch more detail, but likewise, if you're doing manual checks, how often can you spare someone to go and do them? You know.
Yeah. It kind of I would I'd mirror. There's not, again, one nice clean answer for this. It really, you've really got to kind of differentiate between what am I doing this monitoring for an indication of when to take the pump out of service, or am I doing it to avoid let's call it a catastrophic failure? Okay. If you're monitoring it just to do trending, I think you can if it were me, if I'm going to take an average, and I no doubt somebody's going to yell at me for this, I would say that you can take a data point for temperature and vibration probably every hour, or even cut it back from that. Certainly, even once a day for non-critical pump would probably be fine to do trending. What you do want to be careful of if you're cutting back the timing is what I've seen happen is where if the process is changing continually, but your sampling point is kind of fixed, you get this weird data because the pump is operating at a different point each time you're taking a sample. So you do need to be cognizant of that. If you're talking about, yeah, go ahead. Sorry, Mal.
So I was going to say the flip side of that, of course, is if your process is changing throughout the day, you could get what appears to be really crazy, up down type data, where actually it's nothing to do with the pump. It's because the process is, doing whatever it does at that time of day.
Yeah.
Which again comes back to the whole, it depends what you're doing and what you're trying to achieve.
Yeah. Now, I will say that I did write an article on some pump failures where they weren't monitoring frequently enough, and I'll post that in the chat here just now. That was an example where these were pumps handling quite volatile fluids. Either it was boiler feed water, which can flash, or one of them was light hydrocarbon. And what was happening was they were using the API guidance out of if I get it right, I always get it wrong. Let's see here. Apologize, I'm kind of the API has guidance in API 670 on instrumentation for pumps, and it's wrong. It's not to put too fine a point on it. They classify pumps in the same category as centrifugal compressors, which is kind of stupid in my humble opinion and not appropriate. And what happened in the case of here was they would get an almost instantaneous event where the NPSH would drop. Pumps would go into full breakdown and they would break themselves really quickly. And there they were not monitoring the NPSH margin going into the pump. And there you had to be monitoring this essentially pretty much every second to have any chance of stopping the pump in time before it broke itself. So I put that one in there. I mean, it might be an edge case, but at least it's a reference point.
Yeah, I mean, I think some of these extreme cases do illustrate the point well. I mean, I can think of one I looked at out in the North Sea a few years ago now, where I think they had the data sampling cranked up to something like 100 hertz to try and catch what they were trying to catch.
Yeah.
They ended up, I think we ended up with a strobe camera and a white line painted on the end of the shaft to try and prove it was reverse. And it turned out the shaft, I think it was basically a mechanical seal failure on shutdown. And it turned out that the pump was actually, again, valve issue. The non-return valve was slightly sticky. And so the pump shaft ended up actually doing something like quarter of a turn in reverse.
Ooh,
and it was a single spring seal.
Yeah.
So of course, as soon as they turned it back on, there was an almighty crunching
Bang.
noise from the mech seal.
Yeah.
So, but again, they were crazy high sample rates, still couldn't catch anything, and they ended up with a strobe camera again. RCA.
Oh, that's a really interesting one. Yeah.
But as I say, I mean, I've seen plenty where you get like you say, someone with a notepad writing it down once a week, sort of thing.
Yeah. All right, we're at the end of the questions now. I hope we covered them all to your satisfaction. Actually, hang on, let me see. Yep. So I wanted to thank everybody for attending. Those who hung on to the end. I see there's still quite a few of you here. So obviously Ralph and I weren't that boring. So I do appreciate that. Thank you for listening to the seminar. The webinar rather, and I'm on LinkedIn. If you have any follow-up questions, please don't feel shy about asking me. I try to answer them. I can't guarantee I'm going to answer them all, but I certainly try my best. So with that, we'll close the webinar, and thank you everybody for your time and your questions. All right.
Okay.